4.3 is the addition rule for handling situations where we're looking for the probability that on one trial, either A happens or B happens. Now, let me just make this very basic for a second. You told me that the probability, when you roll a fair die, the probability that it lands on 6 is 1/6. What's the probability that it lands on 1? 1/6. So what's the probability that it lands on a 1 or a 6?
2/6, 1/3.
Yes, yes. Took me a second. Yes, 2/6. You added those 1/6 plus 1/6 to get 2/6, and then you can reduce it to 1/3. But when you're looking for the probability of A or B, like landing on a 6 or a 1, you add those two probabilities together. You just have to be careful to not count anything twice. For example, if I'm talking about the number of people in here who have brown eyes and the number of people in here who have brown hair, then there would be some people that got counted twice because they had brown hair and brown eyes. When you're calculating probability, you have to make sure that nobody's getting counted twice. All right, that's the basis of 4.3. Have a little bit of terminology: disjoint or mutually exclusive. Events A and B are disjoint or mutually exclusive if they cannot happen at the same time. That means there's no overlap. In this Venn diagram, the red circle, this red circle is the probability of A. The yellow circle is the probability of B. There's no overlap between A and B in the second picture, so this would be a representation of two events that are disjoint or mutually exclusive. Here, where there's overlap, that's an example where the folks in this orange part are getting counted twice. That's an example of not disjoint. If you say everybody in the red and then count everybody in the yellow, those folks in the orange got counted in both groups. All right, so first let's just practice, is this joint or not disjoint? Disjoint or not disjoint? In a single trial, is it possible to randomly select a subject who is a Republican and at that same time that person be a Democrat? You can't be both. Now, you can vote split ticket, but that's a whole different issue. You have to register as Republican, Democrat, or other. So you can't be, one person can't be both a registered Republican and a registered Democrat. So does that mean those two events are disjoint or not disjoint? They're disjoint because they can't happen at the same time. Number 8, randomly selecting a fruit fly with red eyes and then finding out that that same fruit fly has dark brown eyes. Is that possible? One fly having red eyes and brown eyes? No, you can't have both. Now, don't make it harder than it is. Again, what about the fly that has one red eye and red? Yeah, stop it. This is plural. You can't have two red eyes and two dark brown eyes. So, disjoint or not disjoint? Disjoint. Number 10, randomly selecting someone treated with Lipitor and finding out that same person is in the control group and taking no medicine. Can that be the same person? No, it can't. So, joint or disjoint? Disjoint. And number 12, randomly selecting a college graduate and finding out, hey, that person's also homeless. That could happen. It's very unfortunate, very sad. But does that mean those two events are disjoint or not disjoint? Not disjoint, because it is possible for one person to be in both groups. There could be some overlap there. A complement of an event, new notations, very important. Whenever you see an A with a bar over it from now on, that is the complement of event A, and that's every situation where A doesn't occur, like rain and not rain. The probability of an event A plus the probability of its complement. If there are only two things that can happen, those two probabilities have to add to 1 because one of those two things is certain to happen. So from now on, if I just walk up to you in the hall and flash a flashcard A with a bar over it, you go, that's a complement. A and its complement are disjoint. That makes sense. They can't happen at the same time. Let's look at an example involving complements. From page 156, number 16 says 676 drivers were screened at a sobriety checkpoint and 6 were arrested for driving while intoxicated. In the A part, if I is the event of a screened driver being intoxicated, what's the value probability of I? Well, the probability of I is the same as probability of finding a driver who's intoxicated, and there were 6 intoxicated drivers out of 676. So that's very straightforward. The probability of a screened driver being intoxicated is 6 out of 676. And if you round that to 4 decimal places, it's 0.0089. The B part says, what does I complement represent? Well, if I is the event of being screened and found intoxicated, then the complement of I would be a screened driver not being intoxicated. Or I'm going to say being unintoxicated. Same thing. The C part says, what's the probability of I complement? There's 2 ways you can find that. One is to say if 6 out of the 676 were intoxicated, how many does that mean were not intoxicated? Just subtract and you get 670 out of 676 were not intoxicated, and you can enter that on the calculator, and it's pretty easy. However, it may be even easier since we already know the probability of a screen driver being intoxicated. How do you find the value of the complement of that? Remember that the probability of any event and its complement together, they have to equal 1. So if you know the probability of intoxicated, you can find the probability of not intoxicated by subtracting the 0.0089 that we already have from 1, and you get 0.9911. So the probability that a driver is intoxicated is less than 1%. The probability that a driver is not intoxicated is a little over 99%. And these two together, added together, give you 1 because the probability of any event plus the probability of its complement should give you 1. One other example I added to this page just because some people get stumped when you have a decimal within a percent. That shouldn't matter. To remove the percent sign, you still have to move the decimal 2 places to the left. The question is, if the probability of winning a certain casino game is 0.23%, what's the probability of not winning the game? Again, winning and not winning are complements of each other, so those 2 probabilities should add to 1. If I know the probability of winning is 0.23%, I have to write that as 0.0023 as a decimal. And the probability of not winning is 1 minus that decimal, or 0.9977. So the probability of winning is 0.0023. The probability of not winning is 0.9977. The formal addition rule says the probability of A or B is the probability of A, the probability of brown hair, for example, plus the probability of B, the probability of brown eyes, minus those folks that got counted twice. I don't memorize that like I memorize the quadratic formula in algebra. I just understand what that means and make sure to always remember to count the possible outcomes in a way that no outcome is counted twice, which is what the intuitive addition rule says. Find the total of ways A can occur, the total ways B can occur, but find that total in a way that no outcome is counted more than once. And then when you get that total, you divide it by the total possible number of outcomes, and that gives you the probability of A or B. All right, here's the table. And I'm just going to tell you, you are going to love these tables or hate these tables. It's going to take a little bit of practice to understand how to read them, but tables are a good way of organizing information if you are able to read them correctly. For example, if I say, this is results from experiments with polygraph instruments. If I say, how many people had a positive result, what would you say? It's okay if you're wrong. I just want somebody to tell me a number. 42? If you say 42, then you're right. Those folks did have a positive result, but they're not the only folks who had a positive result. These 15 had a positive result also. So if I say how many had a positive result, that's a whole row. If I say how many had a negative result, that's a whole row. If I say how many actually were lying, that's a whole column. It's not just these 42, not just this 9, but 51 who were actually lying and 47 who were not lying. So for any number on that table, you have to tell me in which of two categories that number belongs. Was the person telling the truth or lying? And then what did the polygraph say, true or false? You have to tell me both of those things. If we're looking for the total number who did not lie, that would be these 47. If we were looking for the total number who did lie, it would be this 51. If I wanted the total number who tested positive, whether they were lying or not, it would be this 57. And if I wanted the total number who tested negative, whether they were lying or not, then that would be these 41. How many people in all took the polygraph test? When you say all, do you mean 57, 41, 51, 47?
No, 47.
Okay, several ways you can do it. Without looking at what I wrote out to the side, you could just add up the numbers here, or this would have to give you the same answer if you added the liars to the not liars. That would have to give you the same answer. Or if you added the positives plus the negatives, that would have to give you the same answer. So there are 98 people who took the polygraph. What does false positive mean? It means something just a little bit more specific than that, because false positive and false negative are both inaccurate readings. So you were half right there, but what's the other half? What's false positive mean? The positive would mean the polygraph said that you were lying, but the false part of that means they were telling the truth. So you wouldn't, I mean, you're getting wrongly accused when you get a false positive. What about a false negative? What does that mean? That's an easy way to say it. The test said negative, but the person was actually lying, so they are getting away with it. In court, which would be worse, a false positive or a false negative? Yeah, I mean, we really try in our justice system not to lock away people who are innocent. That is probably even worse than letting go somebody who's guilty. So this shows why polygraph tests are inadmissible in court. There are, here's a good question. What's the total number of people who got the wrong result? Which would be 24. 24 out of 98, about a quarter of the time, the polygraph was wrong. And that's why polygraphs are not admissible in court. They're not completely accurate. Well, not even, I'm going to say not very accurate at all. If it's wrong about 1 out of 4 times, that's pretty significant. All right, number 18 says, if one of the test subjects is randomly selected, find the probability that the subject did not lie. How many people did not lie? It's not just this 15. They were lying and they were not lying, but the test said they weren't. It's not just these 32. They were not lying. The test said they were. It's the total of this column. It's 47 who did not lie. So how do you find the probability that a subject did not lie? 47 over 98. And if you write that as a decimal to 3 decimal places, somebody punch that for me real quick. 0.480. Anybody second that? All right. About half the subjects were not lying. So the probability that you randomly draw out a subject who wasn't lying is almost a half. It's 0.48. If one of the subjects is randomly selected, what's the probability that the subject had a negative result or lied? All right, let me think about this for a second. I want the probability of negative or lied. The formal addition rule says I would have to find the probability for negatives and add the probability that I got a liar, liar, pants on fire. But then what? If I just add those 2 probabilities and do nothing else, why is that not going to be right? Well, I do have to divide, but something else. There were folks that got counted twice. If I just add those probabilities, what about negative and lied? Lied and negative. These 9 folks got counted twice because they were in this category, negative, and they were in that category, lied. So the formal addition rule, I'd have to subtract off the probability of those who were negative and lied. Subtract off the overlap. Now, I know there's a little bit faster way to do this, but I want you to understand both ways. All right, how many negatives? How many negatives total? This is the negative row. Adam, it's 41. Probability of negative is 41 over 98. What's the probability of randomly picking a liar? Liar, liar, pants on fire. That's these guys right here, 51. So the probability of picking someone who lied is 51 out of 98. But then how many folks got counted twice? 9. Well, no, just these 9 right here that were in the lied column and were also in the negative row. So I have to subtract off those 9. I don't have to enter those 3 fractions on the calculator because they already have a common denominator. When I add them, I know my denominator is going to be 98, and it's much faster to, in my head or on the calculator, punch 41 plus 51 is 92. 92 minus 9 is 83. So 83 out of 98 were either negative or lied. And what would that be to 3 decimal places? Someone, please? 0.998. Does anybody second that? All opposed? Somebody get a different answer? Miss April, what'd you get? Actually, remember that number from last time. Punch it one more time. 83 divided by 98.847, you said, Miss April? There's, yeah. And what was after the 6? So the 6 would, so the 9 would cause the 6 to round up to 7. I say rounded 3 decimal places. That means I want you to have 3 decimal places in your answer. All right. We're going to practice these tables a lot. We're going to do a lot of problems. Hopefully, when I'm talking to you, it makes sense. But then when you get home and you look at it, you really have to think hard about, hey, probability of lying is not just one number, it's a whole column. And probability of negative is not just one number, it's a whole row. All right. Ooh, another table. So I have this one printed as well. Oh. This is a table that summarizes the results of one study of 1,205 people. I'm glad they gave me that number so I didn't have to add them all up, who were asked a survey question. Doesn't matter what the question was, we want to know how many were willing to respond and how many were unwilling to respond. A pharmaceutical company is interested in the opinions of the elderly because they're either on Medicare or soon will be on Medicare. We want to know the probability based on age that each age group would either respond or not respond. In number 28 specifically, we want the probability that someone is over 59 and responded. Nobody say anything for just a second. Stare at the table until God whispers to you. How many people were over 59 and responded? Go for it. I heard different answers. Over 59, that would be the same as 60 and over, right? So there are 251 senior citizens, basically, 251, and responded. That's this whole row. So how many are in both this column and that row? Just the 202. This 202 out of 1205 would be the probability that we're looking for. I'm not going to write that as a decimal. It'll allow us to go just a little bit faster. You know how to do that now. What's the probability that a person refused to respond or is over 59? Oh, you know what? On the previous example with the table, I said there's an easier way, and then I didn't say what the easier way was. Somebody who was thinking, oh, I found it faster than all of this, tell me what you did. Somebody always finds it faster than that. You could just add up the negatives and then add the 42 to it without adding the 9 again. Either you really added the 9 twice, so you have to subtract it off once, or you just don't add it twice to begin with. All right, this plus that would be probability, or that would be the number who were negative or lied. We can do the same thing here, save ourselves just a little bit of time on number 30. What's the probability that the selected person refused to respond or is over 59? What's the first thing we need to find out? Okay, how many people who refused? How do I get that number?
49.
Oh, yeah? Only 49 out of this 1,205 people? The whole bottom row.
59 years there are all.
Okay, but that's not the question I asked, though. I asked, you were reading correctly. I asked, what do we need to know? Somebody said the number that refused to respond. The number who refused to respond, well, all of those guys on the bottom row refused to respond. So I need to add those up real quickly. Is anybody ahead of me and already done that? You are helping me so much. Thank you. And I had a second on that, right? All right. So 156 refused to respond. How many were over 59? Still right answer to the wrong question, Jane. I said how many refused to respond? No, how many were over 59? And that's not just 49, it's what? Total? Yeah, 202 plus 49. Because what the question I asked was the total number who were 60 and over. That's 251. You're still reading the question, but I'm working my way up to the question. Why can I not just add this 156 and that 281 and then divide that by 1205? Why would that not give me the right answer? Because these 49 got counted twice. They were counted in this row and they were counted in this column. So either I can add these two numbers. I need to be pointing here so it shows up on the video. I keep forgetting because I like to walk. I can either add those two numbers and subtract off the 49 who were counted twice, or I can just take this 156 and add the 202 to it. And that way I wouldn't be counting the 49 twice. So I'm just going to say 156 plus 202 over 1205 would be 358 over 1205. It's going to be darn close to 25%. Somebody give it to me to 3 decimal places. 0.297. Do I have a second? Okay, 0.297. And that's all of 4.3. 4.2 was just understanding the basics of probability. 4.3 is using the addition rule to find the probability of A or B. And the main concept is don't count anybody twice and you'll be okay. Now we're ready for 4.4, which is not the probability of A or B, but the probability of A and B both happening on 2 different trials.